All right. Welcome everyone to today's live stream. We have Adam French, and he'll be presenting on the reversibility in mobile automata. So, welcome, Adam.
Hey.
Okay.
Sweet. So yeah, I was looking at over the Wolfram summer school, I was looking at reversibility and mobile automaton. So we'll just go through what mobile automata are to begin with. And then we'll get on to the main topic, which will be reversibility. So I'm sure you guys are all aware of cellular automata.
Oh, yeah.
Yeah. It's quite similar, except let's have a look. It's similar to cellular automata, except we only change a subset of cells at each time step. So the rules typically come up in this form here. This is the case where n equals 3. N is the amount of cells that will be changing at each time step. And we normally change a number of colors. So in the case of 0 and 1, it would be 2 colors, but you could extend it to 0, 1, 2, 3 colors, etc., etc. So as you move to the time step, you change the 3 cells. In this case, where n equals 3, you change the 3 cells around the heads, and then either move left or right. We're restricted to moving only left or right.
Okay, so this is a linear tape with cells in it, and it's like a Turing machine, right? So you have this moving head, that dot in the middle.
Yeah, exactly.
Okay.
It's like a one-state Turing machine, right? Because it's just it's essentially the Turing machine, but with one state. When the head is right.
Pretty much. Later we go on to the equivalence with this and Turing machines, because there is a way of making a Turing machine into a mobile automaton, but it's pretty much a very similar concept. Yeah. So n, the amount of cells, k, the amount of colors, and then we're restricted to only moving left and right.
By one unit, yeah.
Yeah, here's an evolution over some time steps. This is another example of one running, but we know that. Just for this, we need to go through all the inputs that we could have for this machine. So that can be all the combination of 3 cells in this case, just so we have a complete map. So that's an example of another mobile automaton. We have a way of numerating through all of these rules, which will come in useful. Okay, I just need to run another go. Come back to that. Yeah. So this should explain the numeration quite easily, quite quickly. Okay. So dn in this case stands for our direction. So this is where dn is 1, meaning that there's only one rule that moves to the left. But as we increase the direction numbering, you can see it kind of ascends like binary. And similarly for the color numbering, it's another kind of binary numbering.
Right.
But this is extendable. We can do it for any n.
Hold on, is it like there are 2 numbers that enumerate all the single rule, like Sn and Dn? Right?
Exactly.
Usually just one number.
You could turn it into one, but for me it helped to know one distinguishes direction, the other distinguishes color. But yeah, you could do it with one.
Yeah.
It's also because direction becomes quite useful when we're dealing with this. So, I mean, it was more of a personal thing for me. It just kind of helps to distinguish these. Are there any
I
questions?
guess the case for d equals 0, where everything just moves to the right each time.
Yeah.
So it'll
We
like
can-
change stuff and move to the right. That's
Yeah.
Oh, that's there. Yeah, good.
Yeah. So that's the numbering. Okay, so reversibility, this is the main thing that I was working on. So we have this mobile automaton, and we have these rules that tell us how we traverse through it. But say if you give me a arbitrary state, you give me any state and the set of rules that I'm going to be working with. The question is, am I able to reverse this state? Do I know the state that came before it? And yeah, if I have two states that could converge to lead to the one that you gave me, then I don't know which of these two that I came from, because it's ambiguous.
You're saying with these rules in particular, this arrangement is ambiguous?
For this one, yeah. One of the conditions is that we'll get onto the conditions for reversibility because we found all of the rules that necessitate reversibility. But in this case, this would not be reversible because I have these two outputs to be the same.
Ah.
But that,
right. In fact, the first.
Is it allowed to change all three cells, not just the one that the circle is on?
Yeah, all three cells. This is where it's kind of different from a Turing machine.
Oh, I get it. Yeah.
Yeah.
That's all right. So it's not quite.
Yeah, not quite, but it's similar.
Okay. Yeah. Yeah. Good point, Nick.
Good point. Yeah. Are there any questions?
No.
No. Well, I guess there was a K factor. Is that for the number of colors that are used?
Yeah, exactly. We normally have n, the amount of cells we're changing. We kind of require that n is an odd number, because if it was an even number, I can't really have a uniform radius.
Right.
It's like the head cell wouldn't be in the center. It would be somewhere like middle left, middle right. So if n is odd, then we don't run into that problem. It will always be in the middle.
Mm-hmm.
Yeah. Does all this code make sense?
Sure.
We just have a constant array of zeros, and we start off in the middle, and then our time step. And this is just a plot of the rules.
So for the reversibility, is it like sufficient to have a rule that essentially some sort of distinct outputs that has only distinct outputs? Or
exactly.
Okay.
Yeah. So here we go. So because we can only move left or right, if we take an arbitrary state, we know that we could have either come from the left or come from the right. If it's the case that we've come from 2, it's not reversible. If we come from only 1, or if there's only one possible previous state, then it is reversible. And then let's move on to the real deal. Okay, so this is where the proof for reversibility starts, and we'll just come up with a bit of terminology to help us work with this concept. So we have our set of mappings from n cells to n cells, and we're going to come up with two things to begin with, an L rule and an R rule, which are pretty self-explanatory. An L rule will move the head to the left, and an R rule will move the head to the right. So that's cool. And then we're going to come up with these things called blockers. The blocker for an L rule is going to be the n-2 cells on the left, and a blocker for an R rule is going to be the n-2 cells to the right. So in this case, n can be whatever number we want, but the blocker will always emit 2 cells. It will always not include these, but the rest of them will be the blocker. Does that make sense?
Is it
No.
Blocking the progression of anything?
The
or
blocking
you're just
is about
blocking it out, like saying like segmenting.
Yeah, the blocker is going to become useful in just a second, but essentially, let's see if I have it next or before. Okay, but does the idea of a blocker make sense? Like, it's just n minus 2 cells to the left if it's an L rule, and the n minus 2 to the right if it's an R rule. Does that make sense?
No, hold on, it's just the L rule and R rule, right? So you have much larger radius, right? It's not like 3 cells as before.
Yeah, so n can be arbitrary. In this case, we have the n is 7 because we're taking 7 cells to 7 cells. We could have n be 9. Where's the example? Here n is 5. We could equally have, oh, this might break. We could have n to be 7. We could have n to be any odd number. And in this example that I've given, I've said n is 7.
Okay.
So n minus 2 will be the 5 cells to the left of an L rule, and the blocker for an R rule will be the 5 cells to the right.
Okay, got it. Yeah. And so for the case where n equals 3, like this is kind of just like a 1 blocker.
Yeah, exactly. Nice.
All right.
Perfect. So boom. And then here are our full conditions for reversibility. So the reason that we call it a blocker, if you look mainly at these diagrams here, is that we start off in this state here, at the bottom state of this picture. Just going to make it like really big. Okay, it doesn't like that. If we start off on this line, or this state, we could have come from above to the left, or we could have come above to the right. But notice, in both of these scenarios, if we came in from the left and we applied an R rule, then we're going to overwrite this cell here. But that can also be overwritten if we came in from the left. We could have changed the same cell. And that's the blocker. The cells that both a left rule and right rule can overwrite, it's called the blocker. Well, that is the blocker. Sorry, I just... Oh, there it is. One sec.
Very good.
Sorry about that.
Right.
So yeah, and this is the reason why the blocker is important. Is because it represents the set of cells in which both a right rule and both a left rule could have overwritten. So if it's the case that a left rule and a right rule share the same blocker, we could construct the state in which this blocker agrees with this left rule and the right rule. But then we further could make the set of cells on the left-hand side suitable for the right rule. So we, in this case, could make these two cells fit the output of the right rule. And for the left rule, we could make the remaining two cells appeal to the left rule. Sorry, the right two cells appeal to the left rule. And it becomes that if a left rule and a right rule share this blocker region, if both of these cells match for two different rules, then we can't have it to be reversible. Because we can construct a state that will contradict reversibility. And furthermore, we need to have all the right rules are unique, have unique outputs, and all the left rules have unique outputs. Because if this output matches two inputs, then it's ambiguous as to which of the two inputs we came from. This proof is well kind of written out in my community post, but it's proved to be an if and only if condition. So if the mobile automata is reversible, the mobile automata is reversible if and only if these three conditions hold. And the proof is laid out in my community post. Are there questions?
So So what exactly? So that's the motivation, was to distinguish those two types of integers for the direction and for the color, right? In the enumeration, right? So in order to specify that, because naively I would say that reversible rules are those that have just unique outputs without like separating R rules and left rules, right rules and left rules, right? But if you separate it, you kind of have an ability to say something extra about it, right? So it's not just, oh, what's the actual intuition about it? So that to specify reversibility is not enough to just say that the rules has to have unique outputs, right? What does or separation to left and right rules allows you to do? What is actually, yeah, what's the motivation for it?
What's the motivation for this?
Maybe there's like a simple example where it fails, like maybe some set of rules that don't have unique outputs, right? But if you separate into left and right and do this kind of condition, right, it can be reversed.
Yeah, I'm actually not too sure what I mean, the motivation, it seems, is that because this is an only if condition, we have a specific set of guidelines that we need to follow in order to have a reversible rule. So this is useful because then we're able to generate every single reversible rules by going through all the rules that satisfy this condition. So using this, we're actually able to form every single reversible rule. But is that answering your question?
Well, I don't know. It's not clear. Maybe if it's like just, I'm not sure whether is it actually easier to enumerate if you specify like this left and right conditions separately? Is it like much easier to enumerate rules without if you just enumerate it by only restricting to those set of rules that have unique outputs on their own?
Oh, maybe.
So it's not clear to me. It's like what's the motivation for this left and right separation still?
It became useful when proving this because the overlapping region, the blocker region is dependent on having left and right rules. I'm actually not sure, you know.
Okay. Okay, we just ignore it. Let's just go through the rest of the presentation.
I'm sorry if I'm like not completely answering your question. I'll just I'll keep rolling through and then should we see where that ends us up at?
Okay.
Okay. Sorry, I'm so sorry.
You're good. You're good.
So yeah, using these conditions, we're able to generate every single reversible rule. So we have our blockers, and we require that. Sorry if I'm not jumping back and forth, but the right rules and the left rules must have different blockers. If they have the same overlapping region, then it won't be reversible. So first, we're going to partition every combination of blockers to either be left or be right, which then will satisfy 2.3 in this case. So that's what we do first. I get my blockers, which are the n-2 cells in.
Yeah.
We get all the blockers. And then we partition them to be left blockers or right blockers using some kind of numbering. Furthermore, we have the two cells on the left and the right. Because we've done n-2, we just have two remaining to be flexible with. And then to generate all of our outputs, we combine left blockers with this remaining two pair, and then we make sure it goes to the left. And then we get the right blockers, we give it the remaining two pair, and make it go to the right. Oh man, I'm butchering this.
So this is interesting. So I guess in the case of n = 3, the blocker size is 1.
Mhm.
So to have it reversible, you need some sort of saying, okay, well, if there are 2 colors, let's say, then it's like at a position, it's either left or right, depending on the color of the item of the cell.
Yeah, exactly. Yeah.
Okay. And then you would have choice of what that left rule would be if it's white, let's say, and then the black one would be like it would have to go left. It would
Yeah, the coloring of the blocker would dictate whether you came from the left-hand side or the right-hand side.
Mm-hmm.
I mean, I haven't made a visual way of making the reversible rule. Because if you're like following the rule forwards, you're always going to have the head in the middle. So in this case, it goes from the middle to the right. But if we're going back the other way, if we flip this red arrow to make it, you now have the head isn't centered. The head is on the right of the input. So you require the condition on these 3 cells in order to generate these 3. But for some reason, it must be that if you're going back, if you go forward in time, you're going to the right. If you go backward in time, you're going to be going to the left. But you depend on the 3 cells to the left. And similarly, if you were going back to the right for a reversible rule, you depend on the 3 cells to the right of where you are. So like the rules, half the inputs would have the head on the right and half the inputs would have the head on the left, depending on which direction you're going back. Does that kind of make sense?
Yeah. So you would have to look at the blocker, and then once the blocker is determined, you would then have to look in the neighborhood of to the left or to the right.
Yeah, exactly. That's actually
determine
the proof.
where you came from. Okay.
Yeah. So the proof, we assume we have these 3 conditions. So then we're going to first look at this one, and we're going to see the right and left rules have different blockers. So we've assumed this, and then we're going to look at what the blocker will be at our state. Because we're going from 3 to 3, it would just be the cell on the head, which, as you can see, is the blocker in both cases. We'd then know that the blockers are partitioned to left and right. So once we've identified the blocker, we'd know if it's a left or right blocker. And then we're like, cool. Okay, in this case, it will be a left blocker. And then we know that we came from the left-hand side. Oh, sorry, I got that wrong. We identify the blocker. If we see that it's a right blocker, then we came from the left-hand side. And then we further know that...
But we don't see the 2 tips when you're like mousing over that thing. We just see a black rectangle.
Oh, no. Okay, it just says double-click to edit, but...
Yeah, I imagine it's not...
no, but there is
something
alt text specified.
Tooltip, which is going to be annoying. I might... Can I share my whole desktop?
Yeah, go for it.
Is that...
There,
oh,
yeah,
that's better.
That helps.
Yeah, nice. So yeah, if we assume these conditions, we check the blocker. If it's a right blocker, then we came from the left. And then because we know that all the right rules are unique, we know specifically where we came from. And there can only be one because of the uniqueness of the rule. So we can enumerate through all these things by partitioning the blockers and then combining the remaining 2. And let's have a look at what that looks like. Also, there's cyclic tapes, which is where, like Pac-Man, if you get to the very right, then you loop back around. So you can have mobile automaton and cyclic tapes. And for the case of n equals 3, it will be 1, 2, 3. Because when we check to the one to the left of this, it will cycle around to the right-hand side of the tape. Does that make sense?
Yeah.
Okay, nice. So here's an example of a non-reversible rule. And we're going to look at the state transitions on a cyclic tape. And this is what they look like. You can see that for this point here, there are many states that can lead up to that point.
Yeah.
And then from this one, we go to here and follow it around. So that's a non-reversible one. And then we're going to look at reversible ones.
Interesting. So that's a state transition graph.
Yeah. And this is for a reversible one. I'll just run it to make sure. Okay, our scale is going to change. But we use this to reversible MA rule. One of the numbers represents how we partition the blockers. The other number is that the 3 criterion we have, it doesn't actually matter how you permute the inputs to outputs. The only condition is on the outputs. I don't care how the inputs are mapped to the outputs. So the second number, it can just like change the outputs in any way that I want to. So I think I can actually just do this real quick.
Well, don't change the code, just make it like a separate cell. It's a good practice, don't destroy the code that you already written.
Damn it. Okay, I'm just...
Oh, you gotta put a comma there. There.
Nice. So we have a look at that. Like, it's really slow for some reason.
Yeah.
But all of these are reversible. I'm just changing where the outputs go. But because we could, like I said, we can generate every reversible rule. So I can tell you the exact fraction of reversible rules in comparison to all rules.
Wow.
Yep.
And this is just proof of the diagram.
So every reversible rule, its states graph gonna look like this. When there is when there is no in degree greater than 1, essentially, for every vertex.
Yeah.
Exactly. Okay. And so
but this is on a cyclic tape. If it was like we said all of our rules go to the right, but they're also all unique, then I could infinitely go to the right and we wouldn't have a cycle. Like this
is the state tapes. Of the tape for finite tape.
Exactly.
Okay.
Yeah. The finite tape.
Right. All right.
So yeah, and yeah.
So that means that. Oh, that's interesting. Okay.
And then on Turing machines, so we've seen that like mobile automaton, they're quite similar to Turing machines. And I haven't actually covered it in this presentation, but there's a very similar proof to prove all reversible Turing machines where Turing machines are the case where n equals 1, essentially. So there's not this blocker region. However, the only thing that's going to be similar for moving to the right and moving to the left is going to be the states. So for a Turing machine to be reversible, we require that the states are either partitioned to be left states or right states. So if we want to reverse a Turing machine, we first say, okay, we have our 3 conditions for reversibility: unique outputs for moving to the right, unique outputs for moving to the left, but also the states are restricted to being only left states or right states. It's similar to the blocker, where if the blocker is the same for a right rule and a left rule, we can't reverse it. If a state is the same for a Turing machine moving to the right and a Turing machine moving to the left, then we can construct the tape where the state agrees with both a left rule and a right rule, but we can also fill in the cells to the left and the right to appeal to both of those left rules and right rules, meaning that it can have come to it from both moving to the right and moving from the left, and it's not reversible.
Yeah.
So yeah, with Turing machines, I essentially ported over the proof where before I said the condition is on the blockers. On Turing machines, the condition is on the states. The states have to be either left or either right. And using this, you're also able to enumerate all reversible Turing machines. And I tested it on Busy Beaver, and Busy Beaver is not reversible. Okay, I need
2 TM rule. Look at that.
I'm not going to run that because that will like broke my PC at some points.
It'll blow
Oh,
up.
I've
But
written
that
it.
was the plot for Busy Beaver 5.
Yeah. We just checked that Busy Beaver isn't reversible. But that was the plot for Busy Beaver 5, yeah.
Cool.
It's cool, isn't it?
Yeah.
Is it already terminating? How large it is? For
Busy
this one?
Beaver, it's 47 million, I think. But this term,
No,
this
that's.
one. Oh, was it?
You mean how many Busy Beavers there are? I mean how many?
No, how many steps this particular one takes to hold?
I thought it was like
Oh, I haven't
17
run
million
it.
or something like that, and it wrote like 4,000. I forget the
Yeah.
stats on it.
In this case, I've only done the first 100,000 time steps, but it's something ridiculous. I tried to run this on like 500,000 on my PC crashed, so I was like, not doing that.
Yeah.
Okay. Fair enough.
So yeah, this is the reversibility criterion for Turing machines. Let's see if 2TM rule, what's this one? Yeah. So this is for a zoom in hella big. This is for a 4-state, 4-color Turing machine. And similarly, by partitioning the states and then permuting the outputs, we can find every reversible Turing machine. But this Turing machine is like you can't stay in one place. You have to move either left or move right. So there might be like a little bit of I think it just needs closer examination, but yeah, these are all reversible, and that's
I
a
think
number.
Turing machines always move left to right unless unless there is like a halting state. That's the only way it's actually stays in place. It essentially says that halt.
Yeah, it's just because I was reading this book and they were like, yeah, in our Turing machines we have the option of not going anywhere. And I was like, okay, does that mean that I've not got a right representation? So I was just basing it off the book. I
I
got
mean, it
kind of
depends on how you
confused.
define it. I mean,
Yeah.
you define Turing machines that can stay put.
But I'm pretty sure I've got like a valid Turing machine model. So yeah, and then you can check these 3 conditions very easily. And I should have a plot for this. Oh yeah, so I was having fun to myself. I was thinking that could you have like a reversible Busy Beaver? What's the longest running reversible Turing machine? And I thought that could be like a fun problem. So now it's just like find a Busy Beaver, but with the restrictions of these.
Yeah.
I don't know, that might be a fun thing to play with. But this is also like a wild question, but I was thinking if you know that your set of rules is reversible, and you found a final configuration of the tape, then does that mean there exists an input? Yeah, I don't know. I haven't really formalized these questions, but what do you guys think?
But you do have a way to actually run it backwards, right? If you have a reversible rule, you have an actual function that constructs a machine that just reverses it.
Yeah. So I mean, using these and the way in which you actually do the reversibility proof is because we have these conditions on our set of rules. If we want to reverse it, then we'll just follow these. So we'll be like, okay, we look at the state. Is the state a left state or a right state? If it's a left state, then we know that we came from the left. No, if it's a left state, it means that to go back, we go to the right.
Yeah.
So first you know the direction, and then using the direction, you know that they have unique outputs. So you can check your output against. Does that make sense?
Well, it makes, but,
Yeah.
but I want to see it. Do you actually have like a function that reverses a rule? It's like
Not
take
yet, man. Not yet.
no, not
Nah. It's I've just been kind of toying around a bit, but I should write that.
Yeah, it would be like very eliminating example. Just take like a reversible rule, run it for some time steps, and then take that final state, use the reverse rule, and run it again, so that they just look like the flip versions of each other.
Yeah, I did that with mobile automaton.
Yeah, for mobile automata, you can't really have busy beavers, right? Because there's no way to hold, right? There's no
Yeah.
way.
I mean, I was thinking like when it comes to halting, it's just like we don't have this input. It's like in a Turing machine, if you don't have the input, then you automatically halt. You could halt with a mobile automaton if you don't have the input.
Oh, if you
that
don't have a
check-
matching.
Yeah.
But don't you have? I guess there. Yeah, I guess you could. Or I mean, you could have a
Well,
a matching thing that goes to a halting pattern or something, or you can have a situation where it like goes back and forth between.
I was thinking like you just get a whole set of rules for a mobile automaton and then you just delete some like that. And it's like, if you ever get 3 whites, now we don't have anything to deal with 3 whites. So we're just going to halt. Yeah.
Well, I would just like run simulations for a bunch of reversible ones. I see whether find some repeating ones, right?
Mm-hmm.
So some input states that turn into some repetitions.
Yeah. Cycles on a
So those we can essentially like busy beavers.
Yeah, infinite busy beaver, but it wouldn't halt, so that's the problem.
Yeah, we can define it without introducing this extra halting states and all that. You can define like if it repeats the state, it essentially halts.
Oh, like the longest cycle that you could have on a yeah.
Well, the busy beaver is like having the largest transient, right? So you have some cycle, but whatever the largest transient is from the given input, from the like you fix the input, so it's not random. So maybe a single cell, and you run your mobile automata, and whatever the largest transient is, that's essentially like a busy beaver alternative.
Yeah, that's actually quite a good thought. Do I have? I'm just gonna get a little pen. Cool. And so yeah, we started off with reversibility for mobile automaton. You find a similar notion of reversibility for Turing machines, and then that means that you can enumerate all reversible Turing machines. There's a little bit of a caveat that I haven't dealt with though. I've only worked with Turing machines where you need to have all of the inputs filled in. I haven't really dealt with it where you subtract one of these inputs. I still think that you could have reversibility, but it's something that I haven't fully looked into. That's what I was going to be working on. I was just going to make sure that it's consistent with halting states. But with the busy beaver, the halting state, if you go onto the busy beaver website, the halting state is E. But you're only able to get to the state E if you're in the state B, I think. So there's only like one unique place that you could have come from because there's only one transition to state E. You know that before you're going to be in the state that comes to E.
Right.
And like I think that's useful because E is a halting state, and the fact that you know the halting state could have only have come from one place, then It just kind of works in the favor of saying that reversibility doesn't really impact. No, sorry, halting states don't really impact reversibility. Yeah.
Yeah, I think that makes sense.
So what is this slot? Oh, I didn't finish this. Yeah, I just got a few more cool things to show. Oh yeah, this thing.
Oh, cool.
Okay, yeah, so this is cool. So we have this criterion for reversibility, which is C1, C2, C3. So we can check a set of rules and see if it's reversible or not. And when we do that for a specific S and a specific K, I'm just going to like numerate through all the rules using my enumeration, and then check this condition. And you find that reversible rules are distributed like this. I haven't labeled the axes, which I feel kind of bad about, but whatever this axis is, it seems to play a big role. I kind of want to understand this a bit more, but
I think those diagonals are essentially like unique ones. As soon as you get off the diagonal, you introduce some non-unique output.
Yeah.
I think, yeah.
Must be something like that. Let's just see. So for ordering Turing machines, I have three numbers. I have the I have what states are output, what colors are output, then I have which direction arises. Oh, I'm kind of waffling here. I want to stop talking, but yeah.
Sorry. That's really interesting.
And then oh yeah, so this is on a cyclic Turing machine. I've just verified the reversibility. Oh no, what's going on?
No, there's like an L thing. You got to just run the L equals 3.
Oh, perfect. Yeah, so this is for a Turing machine with tape of length 3 that's cyclic. And here I have reversible rules. But I don't have any halting states yet. Like I said, I haven't dealt with halting states. But Nick, yeah, I was wondering, like, if you had a Turing machine, if I got what you were saying correct, it's like a Turing machine with the longest cycle to the same input.
No, maybe not the cycle, but because usually it doesn't have to cycle to the initial state, right? It can cycle to the later state. So you have the transient, which some particular states, and then it starts repeating itself. So it's like transient length from plus the first cycle. That's like the running. So
yeah,
that's the
I think,
number of steps.
I think like this one. So these are non-reversible Turing machines on a cyclic tape. And you have that eventually, if you follow it down, you get to this cycle. These are all black because I haven't filled in the state for these, but is this similar to what you're saying?
Well, we still now two tips are still black, right? So
maybe let's change up the colors a bit.
but the two tip, it's like if it
the
two tip is just a black rectangle.
Oh, yeah. Still. Oh no.
No, I don't know why. I can see your desktop background, but I don't know why this zoom bug.
Let's see if this is gonna. Nah.
You can stop share and then reshare if you want.
Yeah, let's see if that helps. Oh no, I can't see.
Wait for it. No.
Still black.
Damn it. Okay. Maybe I can actually cheat a little bit. Oh man, it's struggling.
What was the idea again?
Yeah, so I was gonna change it from tooltip to just pop out, but I can't even seem to type now. Like I'm hella confused. But it's just the mapping of one state to the next state. Let's see if this will work. There we go. Yeah. So we can see in this example, if we have the cell 0, 0, 0 and the state 1 in position 3, so we're going to be on the left-hand side of this list, then we'll transition to 0, 0, 0 now at position 2, so we've moved to the left. And then from there we go to 0, 0, 0, position 1. So this would actually just go in threes, round and round. But yeah, so this is transient up until we get to this cycle. Is that more what you meant?
Well, kind of. I don't know. Can you even have transients for the reversible ones?
No, because then once you get to the cycle,
Yeah.
you'd have to go in a circle. But if we had one more point coming in,
Yeah.
then that means one of these nodes would have 2 inputs. So you're, yeah.
Yeah, so
I
just
think
the large cycle. Yeah.
Yeah.
Can we see some plots for these automata?
For the cyclic ones?
Sure, yeah, any of them.
Okay, I'm just gonna grab these. We'll do a 2-state, 2-color.
2, 2, 2, 2. Yeah.
I'll just do that. And then state 1, position 1 on a blank tape. And then plot
MA. Plot.
I haven't fully fledged out the plot TM function yet.
Okay.
I've kind of been refraining from using the Wolfram one a little bit just because I kind of like more control. I can quickly make a manipulate. I think. Actually, I might actually have one. But these are on infinite tapes. And oh yeah, here I have used the Wolfram one.
Yeah, looks familiar.
But this is a reversible Turing machine on an infinite tape, and I mean, that's what one would look like. But do you want something more specific?
No, I just want to kind of like look at like more of. I want to see how these things behave, or what the plots look like in general.
Just like cycle, just some random large cycle.
Okay, yeah. Let's get a okay, so I think it's cyclic TM. And I think for cyclic machines, I haven't yet made the tape Oh, it's not expandable. What am I on about?
Well, hold on. What's the difference between cyclic and reversible would be?
There's no difference. I mean, they're kind of comparing two different things, but reversible reversibility is a condition on the rules of the Turing machine. If you take the Turing machine to a cyclic tape, then you can only have a finite number of states or configurations of the tape. But you could also take a reversible Turing machine onto an infinite tape. Does that make sense?
Yeah. So cyclic, it means you just come up with some initial state that just actually cycling, right?
Yeah.
So not necessarily even using the reversible rule. Maybe your rule is not reversible, but you just came up with some initial state that cycles with some non-reversible rules. You still can do it in principle.
Yeah, definitely.
Yep.
I'm just also going to check in some. And we'll look at 20 time steps. Okay, so this is a reversible Turing machine, which we're going to be specifying with Sn and Dn, which are the two numbers that I've used to enumerate all the reversible Turing machines. I'm not going to be plotting the heads at this point. I'm only going to be plotting the tape configuration. I haven't got round to making that into a... Oh, actually... Oh, it's kind of better. And we only want the state, which is the first one. Okay, it's kind of like not really proportionate, but on the left we have the tape, and on the right we have the state.
Okay, yeah, so it starts out as all white, and then it goes into a cycle of gray and black and white, and the all white never repeats. So is that right?
It should repeat. This is reversible.
Okay. So it should go in a cycle.
Yeah, let's just copy this and do it again with a bigger time period.
And what are the ones to the side? Oh, I see. Okay, there's the period right there.
Okay.
It went white.
So it went to all white, but it seems that we're in a different state.
Oh, I see.
So we might need to go even further. It's going to be hella long. Oh man, it's going to be hard to line up these. I don't
Yeah.
think it really is. But let's see if we get 3 white and then a gray in the middle. There's another 3 white. There's another 3. 3 white and black in the middle.
Oh, the
Right.
you get the white.
There we
and then-
go.
Yeah.
So it looks like from this point on, we've done our cycle again. We could actually check that.
Well, with small tapes like that, it's kind of inevitable, right? You always
Yeah,
gonna
yeah,
have
yeah.
this. Yeah. It's
Um,
more interesting when it's your tape is actually infinite.
yeah, I think so too. So yeah, that's pretty much been all my work. In full, it was working on reversibility with mobile automaton. I was more interested in looking at it from Turing machines. And now I have those conditions. And I was just going to play around with reversible Turing machines. I still need to define reversibility with halting Turing machines, because so far I've only dealt with it where we have all the inputs to be defined. As soon as I make that one of the inputs undefined, then it should halt. So I still need to check how that's going to work.
I really like this this that you have.
The setup.
Yeah, the GIF that you have on your community post.
Yeah, the GIF score.
Yeah, yeah.
Yeah, I
Very
didn't
well
get
done.
as nice a graphic for this one, except for this guy. But
Yeah,
but
I
I
mean,
take this with a pinch
diving
of
into what's
salt.
going on here would be interesting.
Yeah. I'm a little bit reluctant though, because like it's dependent on my numbering.
Mhm.
But I mean that seems to give it some kind of structure. Yeah, and that's pretty much it really.
Awesome, awesome.
Seven.
I want to just take a look real fast at sort of these behaviors are interesting. But so this is the mobile automaton.
This one, yeah.
Mm-hmm.
I made a rule that can reverse a state.
Everything is black.
This one.
On me?
Oh, I think I split the window.
Oh.
There we go. But this is mobile automaton.
Oh, I'm not sharing my screen, am I? Wait. Wait.
Oh,
wait, you can't see what I'm
you
doing to
showed
the
this-
live stream.
Yeah.
On Zoom. Right.
The viewers see it, but not. Yeah.
Mm-hmm.
Well, I have.
I'm showing the audience your community post.
Wait.
But yeah. Okay. These are initial states, next states, and the MA. I don't know if you're trying to evaluate all this stuff.
Oh. What's going on here? I was just checking what Yeah, I was wondering what would give you like the biggest circle? If there was a mobile automaton that it only had one big cycle and it didn't have any of these small cycles. That was another question I was thinking of doing.
Yeah.
Or even you could ask the like, what has the most small cycles? Those two could be asked. But just to explain it a little bit more, this is you get a reversible mobile automaton rule. You load it up an initial 11, a cyclic tape of length 11. It's actually not, you know. I'm kind of confused what that is. I don't know why that's there. Is it important?
What do you stay there?
Okay, that was completely unimportant, whatever that MA was. This is on a 5 to 5 MA on a cyclic tape of length 5. And we're going to start off with an initial state. We iterate. We make sure that we deal with every single state that we could possibly be given. We compute the next state that will result from that initial state. And then we plot that in a graph. So effectively, we have, for every state, we find the next one. And then when we join all of these state transitions together, we get big cycles. Just in case the diagram wasn't explained.
Yeah.
Pretty
But yeah.
straightforward. I think making up the one that has the most tiny ones, I think you can handcraft one, right?
Yeah.
I think it's, essentially need some kind of very localized rules that essentially like cycle between the states between each other. Yeah, but when they have cycles like this, it's much more complicated.
Yeah, I think like you said, you could do a lot of left, right, left, right, left, right. Have a lot of cycle length too. And for the big one, you'd have to permute all the outputs. How would you do that? I think you could also handcraft that too. But dealing with the direction makes it a little bit more difficult.
Yeah. Well, another direction that this can take is going into two-dimensional Solar Automaton.
Oh yeah, I was thinking about that. Like, yeah.
Oh yeah. So I've thought about this too, and it's actually fairly straightforward. Because our conditions are that either the blocker can dictate the direction we came from, and in the Turing machine, the state dictates which direction we come from. If we apply it to 2 dimensions, we just require that. So if we can only go left, right, up, down, then the state should be able to tell us whether we came from up, down, left, or right.
Right.
So
So
instead
the smaller radius, like little patch, would be the
so
blocker.
in 1 dimension, we partition the blockers into left and right. But in 2 dimensions, we're going to have left, right, up, down. We need to partition the blockers across left, right, up, down. And then we further have that if we move to the left, then they're all unique. If we move to the right, they're all unique. If we move down, they're all unique. If we move up, they're all unique. So yeah,
Yeah.
first we get the direction from the state, and then we get the uniqueness to find our specific ancestor. So that could, I think, actually go to any finite dimension.
Yeah.
Two-dimensional ones, they'll make some rad animations. If there's
Yeah,
something.
Yeah.
Well, I can't wait to do that.
So let's see. Conceptually, if it's reversible, then does that mean that there's a corresponding mobile automata that is the reverse version of the forward one?
Yeah, so we run into a bit of difficulty, and that's actually also a good question. If we simply swap the inputs with the outputs, we're going to have these weird scenarios where we have a rule, except the head isn't centered.
Okay.
Sorry, if we flip them around, we have the issue that the head isn't centered. We're going to be checking the left 3 cells, and if those are correct with one of our rules, then we can follow that reverse up to the left.
Mm-hmm.
But then if you're reversing up to the right, you're going to be checking the right 3 cells.
Yeah,
but it's just kind
so
of difficult.
it's not a automata with a consistent like lookup radius, lookup neighborhood, I guess.
Exactly.
Like.
But I find it difficult because we could have the say like if this is correct for moving up to the left, what if it's also correct for moving something moving up to the right?
Yeah, that makes sense. Okay, so the reversibility question is complicated. It's leads to something not being defined in the same way.
Yeah. I mean, intuitively, it's because we know that the blocker cell is always going to be a left or right. We can use that to find out if we're going left or right. But in my head, just having the non-consistent neighborhood kind of messes with me a little bit.
Yeah, same.
Yeah. What else could we do?
No, I don't know. I guess we don't have any more ideas. Just some wishes for some cool animations and some functions that can actually reverse arbitrary rules.
Yeah, I want to go into many dimensions. I think that would look really cool. And understanding the structure of this would be really nice to have. But yeah.
Yeah, a lot of those patterns look. Some of them look periodic, and some of them look non-periodic. I'm not sure, quasi-periodic or something like that.
So looking closely to some of those like gaps in there. Maybe would be interesting. What kind of rules they?
And then there's like this obvious symmetry.
That seem like outliers, yeah, like some outliers in there, maybe.
It was quite nice when this like right region came back though.
Yeah, I wonder what's going on there. It's really interesting. Is that one layer of dots or two? Whoa.
One layer.
The right wall looked like it was like there's more than
Yeah, it seems like they're little towers.
Yeah. I wonder if that's consistent throughout the whole structure there, and what that means.
In my community post, though, on the like orange picture, if you look at the very right-hand side of that picture, there'll be like some small black squares, and that was before we knew the conditions. We were kind of brute forcing all this reversible, brute forcing for reversible rules, and those black dots, they end up to be the only reversible ones. But it was kind of nice to like see that rightmost region come back up here in this diagram. It just reminded me of it, and I was like, wow, that's similar. But yeah. And I think that all the rules. Oh, I know exactly what it is. They're all the rules that only move to the left or to the right. I think the in this case the x-axis is the direction, and on the far right we because we start at 1, and we have one of them going to the left. Once we get to the total number of directions, it's going to be all to the left, and then you mod it, and then it's going to be all to the right. Sorry, I kind of butchered that explanation, but yeah. So I've got if we know that a rule is reversible, we want to find the reverse rule. So that's for TMs and MAs. And then we want to hand construct a Turing machine with a lot of small cycles. We want to make a Turing machine with a large cycle, which I think would be fairly straightforward to hand make. And find out more about this diagram.
And maybe about other systems that are reversible. Like there's a Brady asks on the YouTube chat that what, for example, for hypergraph rewriting rules, condition to be reversible. That would be a hard question to answer.
It's a good question though. I haven't actually heard it, but I'd like.
Yeah, that's interesting.
That is very interesting. It's a good question.
Graphs is like really open-ended stuff. Like anything could start happening there. Depends on the restricted rule set you're gonna operate with.
Yeah, there's another question from Brady again. Is there a name for a cell automaton which only updates cells whose above neighborhood contains updated cells? Initial state would be a seed cell. Only updates the cells whose above neighborhood contains updated cells. What does it mean?
I'm not sure what that means. I mean,
there
are cellular automata. I mean, you can define a mobile automata, I guess, to have a lookup history that's more than or it looks at the current state of the tape and then like the previous state of the tape. I guess that's kind of like a version of a two-dimensional automata.
Oh, so it relies on 2 points in time.
Yeah.
Oh, that's also interesting. Yeah, that's really interesting. Yeah. I'm gonna write all these questions down and then put them on the
on Discord.
I'll do it on the Discord. Yeah.
Yeah, for sure.
No? Well then, should we wrap up?
Yeah, let's wrap up. These are good questions and an excellent presentation, Adam. Thank you so much.
Thanks, Adam. Yeah,
Thanks. It was a bit all over the place, but
Yeah, that's perfect. All right.
Oh, yeah. Thanks, Adam, again.
thank you very much. I hope you have a
Thanks,
nice
Adam.
evening.
Yeah.
Cheers. Bye.
Cheers.
Bye.
Bye-bye.